want to make sure everybody really understands what I did here. So the thing to keep in mind is that the width of the rectangle, or I guess I could call it length, it doesn't really matter. Width of rectangle is equal to 120 minutes. Now how do I get that? It's 3 to 5 p.m., which is 2 hours. Okay? Now the height of the rectangle is what we want to know about. Okay? Well, I know that the area of the rectangle has to be 1, right? Because we assume that the cable repair person must show up in that time and all the minutes are equally likely. And if that's the case, the probability of showing up during any 1 minute is equal to any other minute. Let me put it that way. Okay. So the sum of all the minutes must be 1. Right? That's the rule from chapter 5, that the probability for the entire sample space has to make 1. So if we know that the area is 1, but wait a second, area is equal to, let me bring this down for a second. Area is equal to width times height, or length times height, or whatever. Length times width, doesn't make any difference. Width times height. But we know that it's 120 for the width. So what must the height be? Right? Well, that would mean that the height is going to have to be 1 divided by, so I'm going to put right down here, 1 divided by 120. It'll always be 1 divided by something. So if they had given you 1 hour, it would have been 1 divided by 60. 2 hours, it's 1 divided by 120. 3 hours, it's 1 divided by 180, and so on. Okay, so that's the height of this rectangle, is 1 over 120. Now, where does that help us? Well, that helps us with the next question. So, oops, I don't want to give away the answer here. All right, so what is the probability of the cable repair person will show up between the 10th and the 25th minute? And I drew it for you in a little shaded box here. So there's the 10th minute over there, the 25th minute over here. But when you're looking for the probability, what you're really saying is, what is the area of this bar that I just drew right here? Okay, well, since it's a rectangle, we know that it's length times height, or width times height, whichever. Doesn't make any difference. Okay, but the width is 25 take away 10, because 25 is over here, 10 is over here. So you subtract and you'll have the width. And then you multiply it by 1 over 120, because we know that that's the height, because we found it up here. All right, so that means that's 15 times 1 over 120, which is 15 over 120, which is 0.125. All right, and then they ask, what is the probability of a cable person shows up exactly at the halfway mark? And I just wrote it down here. It's a trick question. So the probability exactly at 4 p.m., exactly at the instant of 4 p.m. is 0. Now let me see if I can show you why. If I go back and look at the graph for a second, let me just delete this part. Okay, there's the graph. Where is 4 p.m.? Well, 4 p.m. is a line. Let me draw it right here. X equals 4. And it has, I'm just going to make it a little wide here so you can see it. Oops, there it is. Hold on one second. There it is. Technically, this has no area. It has no width, right? It has length, but it has no width. It's a one-dimensional object. So it has 0 area, right? Therefore, 0 probability. Now, if they had said between 4 and 401, that would be 1 divided by 120. But when they say the word exact, they mean at that instant, not a minute, like a moment. And a moment has no time, has no area. Therefore, it can have no probability. So that's the big difference between continuous distributions and discrete distributions. Discrete does exactly things all the time, but continuous you can't do exact, because exact ones have no area.